I was standing by a creek last summer, and I saw this perfect little whirlpool form behind a rock.
Mm-hmm.
And it just struck me how much invisible physics is driving something so simple. You see it in a tornado, a smoke plume. It's all about vortex stretching.
It is.
So today, we're doing a deep dive into that very dynamic. We're exploring one of the biggest unsolved mysteries in physics and how the answer seems to be, of all things, geometry.
And to really get into it, we should probably start with a simple idea. Vorticity.
Okay, what is that exactly?
It's just a measure of the local spin in a fluid. Imagine a tiny paddle wheel placed in the flow. How fast it spins. That's its vorticity.
And vortex stretching is what makes it spin faster.
Precisely. The classic analogy is a figure skater.
Pulling in their arms to speed up.
Exactly that. When a flow compresses a vortex tube, along its axis, it forces that rotation rate to just shoot up. That stretching is what powers turbulence.
And there's a perfect real-world model for this, right? The Berger's vortex.
Yes, the Berger's vortex. It's so important because it's an exact, stable solution to the Navier-Stokes equations, the ones that govern real fluids with viscosity.
So it shows how a stable system like a tornado can even exist.
It does. It's this beautiful three-way balance. You have inward flow concentrating the spin, you have axial stretching making it spin faster, but you also have viscous diffusion.
Friction.
The friction, yeah, spreading it all out. When those three find an equilibrium, you get a stable column.
Okay, that makes sense for the real world. But here comes the million-dollar question, literally part of the Clay Millennium Prize.
Mm-hmm.
What happens when you take that friction away? In the pure inviscid 3D Euler equations, can the flow just blow up?
Mm-hmm.
Can it form a catastrophic singularity?
That is the question. And for decades, the mathematical expectation was, yes, it should blow up.
Why?
Because that stretching term is violently nonlinear. It's quadratic in vorticity, which suggests this explosive runaway growth in energy.
But that's not what we're seeing now.
Not at all. And this is where high-resolution computing has just completely changed the game.
Right, you heard those sources on the work from Ho and Lee. They're looking at these anti-parallel vortex tubes.
They are, and they are running these simulations at just mind-boggling scales.
What are we talking about?
Up to a grid of like 1536 by 1024 by 3052 points. Billions of points.
Wow.
And you need that resolution to see what's happening. And what they found is stunning. The vorticity, it just doesn't grow faster than double exponential. It suggests a non-blow-up scenario.
So here's the key insight for you listening. The math predicts a catastrophe, but the simulation shows it. Just doesn't happen. Why not?
It all comes down to the local geometry. As these intense vortex tubes evolve, they start to flatten out. They become these very thin vortex sheets.
And that change in shape is the key.
It seems to be. That regularity, that flattening, it causes what they call a dynamic depletion of vortex stretching.
The geometry itself acts like a brake.
Sort of, yeah. It's a self-correction mechanism. It prevents the singularity and keeps the whole system's energy bounded.
And it takes that incredible computational power just to watch the physics fix itself.
You really need these advanced modeling tools to make these fundamental discoveries.
You know, that complexity actually reminds me of our sponsor for this deep dive. This is all brought to you by Embersilk. If you're tackling complexity in your own work, maybe AI training, automation, or software development, Embersilk can help you figure out where powerful agents could make the most impact. You can check them out at embersilk.com for your AI needs.
And speaking of complexity, there's actually another big paradigm shift happening right now.
Oh.
It's about the turbulent energy cascade. That's, the way energy moves from big motions down to the tiny scales where it finally dissipates.
And for decades, everyone thought vortex stretching was the main driver for that, too.
It was. It was considered the primary mechanism driving that average energy transfer.
So, if we're now learning that stretching gets depleted in that critical moment, and it's not the main driver of the average cascade, what is?
Well, the new research points to something else. Vortex stretching seems to be responsible for the fluctuations, the sort of spikes and dips.
But not the steady flow of energy.
No. The primary driver of the average cascade is now believed to be the self-amplification of the strain rate field.
So it's not the spin itself, but the stretching and compressing of the fluid around the spin.
Exactly. It's the field of shear and compression surrounding the vortices that governs the overall flow.
That is truly inspiring. This journey into 3D turbulence shows that what we think of as the most chaotic flows aren't just ticking time bombs.
Not at all. They're governed by these elegant, self-stabilizing rules.
From the Berger's vortex to this geometric self-correction, it feels like the more we look.
The more we find these sophisticated mechanisms ensuring a sort of coherence,
Yeah.
even in the chaos, there's an inherent structure just waiting for us to find it.
So what does this all mean for you? It means our ability to model these systems shows that even the fiercest flows, like in the core of a hurricane, are governed by these beautiful, surprisingly resilient rules. It hints at a deep underlying order in the universe. If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.